Oh, welcome to class, everybody. We're going to learn about IVT. This is day 2. IVT is a very, it's like a concept that you know happens, you just never really thought about it. Really, it just I'll just read the first example before I really explain it. So let's just say that the height of a child from age 5 to 10 happens. So let's say that you're, what's an average height at age 5? 45 inches? 45 inches maybe? I don't know. And then at age 10, you become, 55 inches. So as you're growing, don't you hit every single inch? Right? At some point, you hit 46. At some point, you hit 47. You don't just jump. You're not just there, like Neil's just sitting there going, oh my gosh, it just happened. I just went 1 inch. It does not happen that way, okay? So IVT just says, as long as the function's continuous from one endpoint to the other, it's going to hit every single point. Okay? So, I don't know if I'm supposed to be like drawing on this or whatnot, but let's say this is like a child here at age 5. So we'll just say that this is age. And we'll just do height in inches. So what would we say? Like 42 or 45, doesn't really matter, to 55 inches. I think it's a pretty tall 10-year-old. 55 inches, that's like 5'7". That's pretty tall. Anyway, for a 10-year-old, that's really tall. Alright, so we start here, and we start here. Okay? I don't really care how you draw this. You can go up high first and then slow down. You can kind of just do it. Obviously, you should be decreasing unless this kid has a major problem. I guess if they have surgery, but that would be continuous then. Like if someone just chops off their feet. It's no longer continuous. So, I don't know, like this. It doesn't have to be a straight line. It can be a little curvy. But it's going to hit every single point. Okay? So that's what the IVT states. It says, hey, it's just going to hit every single point. And these are the 3 things you need to state for the IVT. Because it's going to ask you, hey, is it possible for this to happen? 90% of the time it's a yes. You need to state why it's a yes. I'm aware it's stupid. I know, I saw his graph and it's stupid. I didn't see his graph. Yeah, I should just put a mirror up there so I can see all the work you're doing. Okay, so you have to state these 3 things. You have to state 1, boom, it's continuous. You have to state that the 2 values are not equal, the 2 endpoints. Because if the 2 endpoints are equal, then IVT doesn't really work. And then at least 1 number between them so that every single value is hit. So I just really would like to get to an actual problem. So do we get the idea of conceptually what it is? Okay, we got the idea of conceptually. So let's go ahead and just go right to 16. We're just jumping around here. I get to the important stuff. So verify that IVT applies to the indicated interval and find the value of C guaranteed by the theorem. So I have to state first what was my first statement? So is f of x continuous? You do not need to show any work for it. You get the benefit of the doubt. It's continuous. It's a polynomial, so it's continuous. What's the second thing you have to do here? So find f of a. Well, so the endpoint. So what is f of 0? So plug in a 0, you get 0 squared minus 6 times 0 plus 8. 8. Okay. And what's f of 3? So you get 3 squared minus, so it's 9 minus 18 plus 8, which is what? Negative 1. So, do we agree that at some point the function is going to equal 0 between 0 and 3? right? Because here's this function. I'm not going to know exactly what the function is, but we are, I'll just draw the whole graph right here. So at 0, we're at 8. We're here. And at 3, let's do 3 here, we're at -1, which is right here. And this is continuous. So at some point, it's going to hit 0. You agree? So it's that last thing that we say there. We're going to say that. So now the conclusion is there exists a C value such that f of c equals 0. So this is just a verification. Okay, it's all we're trying to do. We're just trying to verify. That's the first part, because there's an and, right? So we just did the first step, verify. So we verify that there's a c. Part 2, find c. How do you find c? Well, you set the function equal to, in this case, 0. Let's go ahead and do that. So we're going to get x squared minus 6x plus 8 equals 0. And our answer has to be between what two numbers? 0 and 3. Our c value. So let's go ahead and do that. Well, this one you just factor, right? You get x minus 4x minus 2, is that correct? So x equals 4 and x equals 2. Are both those correct answers? No, why not? Okay, so we have to graduate to our c value. So do we have our two x values? Do both of them graduate, or does only one of them graduate to a c? Only one of them. Which one graduates to a c? 2. And why is that? Because it's between 0 and 3. It's in the domain. X's. So that's our c value. So at some point here, it's going to hit. Alright? I don't really know exactly how this is going to work. Well, I guess I probably could. That's probably the vertex right there. Alright. I'm sorry how this packet printed out like so poorly, but it's the exact same question for 17, and then all the stuff's on the other side. Alright, so we're going to do the same exact thing here. The same 3 steps. So we have the function f. We have to verify the IVT. What's the first thing I have to do? Say it's continuous. I mean, we can just say it, but is it continuous? Yeah, it's polynomial. Now, sometimes it's not continuous entirely, but you have to make sure it's continuous within that interval. Like, if I had the like 1 over x, that's not continuous. But if I have an interval like from 1 to 2, it's continuous in that interval. So fx is continuous. We'll just say in the interval from 0 to 3. Step 2, f of 0 is equal to 3. F of 3 is equal to, oh, this is annoying, 27 minus 9 plus 3 plus 3. So what is that? 24. So there exists a c value. Alright, what exactly did I say last time? There exists a c value such that f of c equals 4. So that's the verification. Now let's find out what it is. So we're going to set x cubed minus x squared plus x plus 3 equal to 4. So let's move all the constants together. So I have x cubed minus x squared plus x minus 1 equals 0. This is better. Okay, this factors. How do you factor it? Starts with a G and rhymes with grouping. Grouping? Grouping. So, do the first two have a GCF? Of what? So it's x squared becomes x minus 1. The second one has a GCF of just a 1 so I can match it. So it's going to be plus 1. X minus 1 equals 0. So I'm going to get x minus 1, x squared plus 1 equals 0. And that second parentheses, will that ever equal 0? No, so I'm not worried about it. What about the first parentheses? Yeah, x equals to 1. Does it graduate? Is between 0 and 3? Yes, so C is going to equal 1. Questions on this? Question on the concept? Again, it's writing three things. A lot of calculus is there's three things that it needs. There's three things. So continuous, we got our three things. IVT, we got our three things. When we get to more stuff, you'll see. Oh my gosh, there's three things. I'm gonna skip 18. 18 is like the same type of problem, so I'm not worried about it. Let's just go right to 19. This is like a type of problem you'll see like a multiple choice or something like that. So it says a car runs back and forth continuously for 20 minutes on a section of a straight highway. That car's a jerk. Like, was it just like on a highway going like this and that? Who does that? The car's velocity measured in meters per minute is given by VFT, where the time is measured in minutes. Selected values are given on the table below. Do the data and the data in the table support the conclusion the car's velocity is negative 47 meters per minute at some time between 5 and 11. Give a reason for your answer. So I'm only looking right here. This is all I really care about. So, bro, let's just quickly see what this car is doing. So from 0 to 3 is this minutes. 0 to 3 minutes. They're going anywhere between stops to going 80. What is it? Meters per minute. I don't even know if that's fast. Is that fast? I don't know. 80 meters per minute. No. I don't know. Okay. And then at 5 seconds it slows down to 20. And then by 11 it's going negative 90. That means it went into reverse at some point and it's not going the other way. It's like as if we put like a kindergartner in the car and is driving it. Granted, I don't think I could figure out how to get in reverse. So this is just kind of a weird situation. Calculus loves these really weird situations. But can we guarantee that at some point between 5 and 11 this one was going negative 47 meters per minute? Yes. How do we verify this? We do 3 steps. What's the first step? VFT is continuous. How do I know that? It says it. The second step. Take my endpoints. What's the V of 5? What's the V of 11? So because of that, there exists a C value. Or actually, we already know the number. So we'll just write the same thing we've done. C value. Again, I forgot my exact verbiage. I'll write it up here. C value such that V of C is equal to negative 47. And that's what you do for IVT. Questions on IVT? You'll get a chance to practice independently when we get to our worksheet. So we're going to move on. Today's kind of a faster day with materials and stuff. We're going to get to now evaluating limits without graphs. So, I know, it's exciting. So whenever you evaluate limits as just a function, there's a couple steps involved. The first step is you always plug in directly. You always plug in directly. And if you get a number, great, you're done. If you get 0 over 0, then you got some work to do. If you have like some number over 0, you got some work to do. Okay, so we're just praying when we plug these numbers in, we get a number. Which only happen like one time. Or maybe a couple times here. So let's go ahead and do that. So number 20. I'm going to plug in a 1. Do I get a number? Yeah, so this is pretty cool. So I'm going to plug in a 1. So it's 3 times 1 cubed minus 2 times 1 squared plus 4. Which is 3 minus 2 plus 4, 5. And that's it. We're at 21. Plugging in a 1, does that give me a nice number? Oh my gosh, it does. Alright. See, calculus is so easy. What do I get? 4 over 2? Which is... $22. Is plugging in a 0 work? Oh, how nice is that? So I'm going to get square root of 0 squared plus 4, which is... root 4, which is 2. No, because you only do that when you're solving for x. It's when you have x. $23. Does directly plugging in work? Right, you're probably thinking right now, it's getting too easy. Don't worry, I'll get harder. Plug in a 3 directly. You get cubed root of 8, which is no big deal, right? $24. What happens if I plug in a negative 3 directly? You get, well, 0 in the denominator and in the numerator. I use arrows, by the way, so that's 0 and that's 0. You cannot write equals 0 over 0 because that's not true. It doesn't equal that. We're going to find out what it does equal. So this just means since there's a 0 on the top and the bottom, that there's a hole of some sort. So what do we do to get rid of holes? You have to factor and cancel. So does the top factor? It should. How's the factor? And the bottom just stays the same. Now, we need to keep writing our limit notation. You'll get points taken off for this. You stop writing limits as soon as you plug in. You have to write your limit notation until that point. You keep writing down limits. On the first 4, I did not write down limits. Why is that? I plugged in immediately. I was good. So how does this simplify? So now I have the limit as x approaches negative 3 of x minus 3. Am I ready to directly plug in now? Yes. So I'm going to get negative 3 minus 3, which is... oh, x minus 2. Who told me 3 at first? Myself? Yeah, probably. Alright, this looks better. I was just trying to keep you on your toes. Yeah, right. Alright, what's negative 3 minus 2? Negative 5. 25. What happens when I plug in 4 directly? 0 on top and on the bottom. So how does this factor then? X minus 1, x minus 4. On the bottom, x plus 2x minus 4. And what do I get? Those cancel out, so I'm plugging in the limit as x approaches 4. And am I ready to plug in directly now? Yeah, because I'm going to get 4 minus 1 over 4 plus 2, which is 3 over 6. Oh, by the way, in calculus, on free responses, you can actually leave that answer. You can leave 3 over 6 full credit. Just a heads up. You don't have to. I mean, like, I have OCD, so I'm going to. But you don't have to. There are some problems where, like, I advise you don't, because the numbers get, like, they're pretty heavy. And if you just, and I have had students that have the correct work. They have, everything is correct. And if they simplified incorrectly, no credit. There are kids that just stopped. Whatever, that's good enough. Coach Meyer said that was good enough. And they had full credit. So it doesn't hurt just to stop. So this is the correct answer. I'm just kind of giving you a heads up on that information right there. Let's see here. Okay, it doesn't get too much more complicated than this. Okay, do you want me to go through 26, 27, 28? Or are we good? We're good? All of these produce a 0 over 0, but yes, it is a different situation. Do any of these produce zeros? All of these produce zeros on the top as well. Yeah, and we'll talk about that on tomorrow. Yeah. Let's see here. Okay, there is another type of problem. I do want to go over it. I'm going to kind of like get rid of these. I'm going to do a different problem. Let's do the limit as x approaches, I don't know, let's do 2. Square root of, let's do x minus 1. I'm just making a problem up. We'll call this like number, I don't know, number whatever. So this one, what happens if you plug in the 2 directly? Zero and 0. Okay. So this is not a problem you have to know how to do. It's not in your notes. It's not in your worksheet. So I'm going to just give it to you here, and I'll give you another problem to practice. So you get 0 over 0. Can you factor this? No, but there is another way that we can go ahead and tackle this problem. Anybody heard of the conjugate? The conjugate. What happens when you multiply by the conjugate? X minus 1 plus 1. X minus 1 plus 1. Am I bro? Oh God, no! This is like a basic one. Nothing here has been complicated. This is not complicated. All right, I've taught BC calculus, so I know complicated. This is not a BC topic. This is an AB topic. And BC. It's both. It's not an exclusive BC topic. Okay, at my old school, I taught pre-calculus kids how to do this one. Yes. It's not that hard. Okay, we're going to go through it, and they're going to be like, oh my gosh, it's so hard. I'm going to do another example, and you go, oh, it's the exact same thing. Okay? It's not that hard. So when you multiply by the conjugate, the beautiful thing about multiplying by the conjugate is there's no middle terms. They get canceled out. That's the beautiful thing. So what's root x minus 1 times root x minus 1? X minus 1. What's negative 1 times positive 1? Negative 2. Again, I'm still my limit notation. Oh, sorry, I'm skipping ahead. It's 1. Okay? It will turn into a minus 2 in a second here. But it's x minus 1 and then minus 1. That's on the top. On the bottom, I suggest you do not distribute. Otherwise, you're going to have problems. So leave this as x minus 2, and then on the bottom, root x minus 1 plus 1. Leave it that way. Why do you think I should leave it that way? Because you're going to end up canceling out. Because if you distribute it, then you would need to factor it, which is really difficult to do with the square root, and then you need to cancel it out. So what's the top turn into? It turns into x minus 2. So what can I do now? Cancel those out. So I'm going to get the limits as x approaches 2 of 1 over root x minus 1 plus 1. Am I ready to directly plug in now? Yes. When I plug in directly, what do I get? 1 over root 2 minus 1 plus 1. Well, what is 2 minus 1? What's the root 1? On the bottom, what's 1 plus 1? It's 1/2. Do you want to try one all on your own? Yeah.
So how would you figure out if like a limit was undefined?
So undefined, like it does not exist.
Yeah, like let's say the particle outside the
That'll happen on piecewise functions and whenever you have asymptotes.
Oh, so just not.
Right. So these problems, it's not going to happen unless we have piecewise functions, which is coming up in just a moment, or vertical asymptotes, which I don't think we talk about until day 3. Okay. Why don't I just give you another one? You can practice on your own. Yeah. Let's do the limit as x approaches, I don't know, pick a number, smaller number. 3. Do you want to put the radical on the top or the bottom? I don't really care. Bottom? Okay. Let's do x plus 6 on the bottom. Let's do minus 3. Right, that will give me a 0. And then x minus 3. Okay. So I want you to go ahead and practice this problem, knowing it's the exact same steps as the problem we just did. It is like the exact same problem. I just changed some numbers up. It's not that big of a deal. So go ahead and give it the old college try. I'm going to do the work as well. You can kind of see. You can't see that at all. I don't have any blank space. It'll be fine. 9. So this is what you should get in your second step. X minus 3 on top with that conjugate, and on the bottom should be x plus 6 minus 9. What does the 6 minus 9 turn into? A negative 3. So this x minus 3 is going to cancel out with that bottom right there. So we're going to get the limit as x approaches 3 of root x plus 6 plus 3. So the final answer is 6. So plug in the 3, you're going to get root 9 plus 3, which is equal to 6. Now, is that problem that difficult? No. No, this is basic. I taught on level, remind you, on level pre-calculus kids.
Is there a big difference in on level?
There's no on level calculus. No. 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 Hey, number 29 kind of got cut off. I'm not too worried about it because all these problems are the same. These notes, they get fairly repetitive, so I'm just going to start skipping around a little bit. Let's just do number 30. Okay, so for number 30, this is a piecewise function. So this is where you might get something kind of weird, where it does not exist. So the right and the left need to match. The right and the left need to match. So to find the limit as x approaches 3, we have to find 3 from the left, 3 from the right. And luckily, all of these are just direct plugins. They're nothing that complicated. So the first one here in 30, we're going to do 3 from the left of f of x. Which one is the left, the top or the bottom? The top, because we're looking for values that are less than 3, less than left. So we're going to do 3 times 3 minus 5. Okay. This is the left on top. This is the right on bottom. What is 3 times 3 minus 5? 4. Let's do the limit as x approaches 3 from the right of f of x. So I'm going to get 3 squared minus 5, which is equal to... So guess what? The limit as x approaches 3 of f of x is equal to 4. So for all these piecewise functions, again, they're all the same as you do the next two problems. I probably won't do the next two problems. But they're all the same. Actually, no, I will do the next two problems. The right and the left have to match. If they don't, it does not exist. You don't need to explain why if you show the work. So you're good to go. So for 31, we're going to do the limit as x approaches negative 2 from the left of this f of x. Which one's the left, the top or the bottom? So we're going to do negative 2 minus negative 2 plus 3, which gives me an answer of 7. Let's do negative 2 from the right. You get negative 2 squared minus 5, which equals... Which is negative 2 squared?
4.
Minus 5? Something that's not a 7. Yeah, negative 1. So what can I say? D and E. And that's enough work for me. Bless you. You don't need to because you just did all the work. Remember how we explained it? We would say that the left-hand side and the right-hand side do not equal. And we just did that. 32. Am I going too fast, by the way? Good. If you said yes, I still wouldn't care. Because we got things to do. Okay, 32. Well, I got another page of this. Yeah, it's got another page. Okay, it's not too long. It's not bad. Okay, so for 32, this one's a little bit different. Why does 32 look a little different than the 2 we just did?
There's no code.
There's no there's no inequality saying that this is the left, this is the right. So because of this, isn't the top just a polynomial? And all they did was they just took a value out and put it somewhere else. So we would call this removable, right? Do we agree that this is a removable discontinuity? So in a removable, the right and the left are always equal in a removable. Do you agree with that? So in this case, the limit as x approaches -4 from the right of r of x is equal to the limit as x approaches -4 from the left of r of x. It's because this is removable. It's a hole. It's not jumping. If this were a jump, like this, like 31 is, then yeah, it's gonna be DNE. So it's a hole. It's removable. That's fine. So I can go ahead and evaluate it. Since I know that this is true, I can just evaluate it right off the bat. So plug in a -4. So the limit as x approaches -4 of r of x is equal to 2 times -4 squared minus 3. You are just doing a direct plug-in. What's -4 squared? 16 times 2. 32 minus 3. 29. I'm going to try to finish everything in the next 3 minutes because I think everything we're doing can kind of go that quick. We good? Okay, tables. It's a real quick conversation about tables. So when we do tables, all we do is we look for numbers that are approaching 2 from left and from right, see if they match up, and we get our limit. So on letter A, you see how these values are getting closer and closer to 2? So this is from the left, and this one is the right-hand side. So what values do you think that's going to be? Equals to 1, right? See how they're both approaching a 1? I'm just trying to help you read the table. That's it. Letter B. This is kind of a weird one. Do I care about the exact value at 2? No. Do I care about this? I can just cross it out. I don't care. I care about the limit, the approximation. So from the left-hand side, what number is that approaching? Right-hand side, what is that approaching? They're the same. So the answer is? But coach, it should be 12. Why isn't it 12? Because the limit's an approximation. This is actually removable discontinuity. Alright? Like I said, it went pretty fast. Let's keep going. Let's talk about trig. We need to know trig values. So that's what all of this is getting you back into trig. I'm not going to do all of these, but you just need to know what they are. We're coming back to trig. So for 34, these are all direct plugins, by the way. For 34, well, actually, maybe not all of them. We'll see. If I plug in a 0, what do I get? What's tangent of 0? No, it's 0. We need to know this. If you need help on this, come see me in tutorials. We don't have time to waste. It's 0. What about the limit as x approaches pi of x times cosine of x? Can I just plug in directly? Yes, I'm going to get pi times cosine of pi. What is cosine of pi? It's -1. So it's pi times -1, which is negative pi. Next one, we're going to plug in directly. We're going to have e to the -0, which is the same thing as 0, times sine of pi times 0. We're going to get 1 times 0, which is Are we remembering trig? Yeah. Oh, yeah, that's probably a great idea. 37. Let's go ahead and do sine. What is sine of 3 pi over 2? And then we're going to square it. It's negative 1. So squared. So it's negative 1 squared, which is 1. This next one might be a little bit tougher. What's cosine of pi over 2? What's cotangent of pi over 2? It's 1 over tangent. Okay. So we get 0 over 0. I can't factor it. I can't conjugate it. No, it's 0 over 0. Remember when we did that proofs unit in pre-calculus? And like, when are we ever going to use this? Yeah, now. How can we convert cotangent into something else that we like that's nicer? It's cosine over sine, right? So this is the limit as x approaches pi over 2 of cosine of x over sine of x. So doesn't this equal the limit as x approaches pi over 2? So you're dividing, so you flip the second multiply. So this is going to be cosine of x times sine of x over cosine of x. Correct? Pew, pew. Cancel out. Now I'm ready to plug in directly. What is sine of pi over 2? It's 1. Last tiny little thing. I'm just squeezing in there, just squeezing it because of time. Oh, it's a squeeze theorem. Hey, this is another theorem that's common sense, okay? So if you have these two functions, just please listen up. If you have these two functions, one function is always greater than or equal to the other function. If they have the same limit at the same point, that means they come together at one point, and there's a function in between it, it's going to have that exact same limit. So in this case, look at, I have a function h, a g, and an f. H is always bigger than or equal to f, okay? And g is in between this. Here, I want to grab one of these. So this just means that the limit of all of these is going to be equal. That's all that means. Okay? So that's 39. I'm telling you that this statement is true right here. Find the limit at 0. So all we have to do is plug in a 0 into each endpoint. And if they match, that's the limit. If they don't match, then you cannot use the squeeze theorem. The squeeze theorem does not work. Okay? So is the squeeze theorem going to work here? I plug in a 0 into here, what do I get? 9, which is 3. Plug in a 0 here, what do I get? Root 9, which is a 3. So f has to be what? If f has to be between 3 and 3, it's 3. And then for letter B, we have the function plus 25. Well, we found this out. What is the limit as x approaches 0 f of x? And then we're going to add that to the limit as x approaches 0 of 25. Well, didn't we just find out that answer right there? What is that answer? So 3 plus 25 is 28. Okay, I know that was a lot. A lot was in there. Here's a worksheet. Work on as much as you can right now.